Machine learning models in ML domain are many a times overfitted or underfitted, due to improper trainings on data set. An overfitted model predicts correctly to the training data set, and incorrect prediction to the unseen data set. On the other hand, an underfitted model does not predict correctly even to the training data set. However, a well-trained model or good fit model predicts correctly to the unseen data set. Let's understand the concept of overfitted and underfitted model one by one using some example. Take the case of overfitted model. Say, Mr. X is at source point A. And he wants to move down to destination point B. Very first path to reach destination point B is 1, 2, and 3. Call it as path 1. Second destination path is 4, 5, 6, 7, 8, 9, and 10. Call it as path 2, and the third destination path is 11, 12, 13, 14, 15, 16, and 17. Call it as path 3. Mr. X is trained to reach his destination point B using the path 1 only along with some path deviation noise. Let's add some deviation in the path in form of noise. Noise N1 means, if Mr. X is at N1, and he can manage to reach his destination B. This means, Mr. X is trained on noise N1. Same way noise N2. Mr. X can accommodate the noise N2 also. Further, noise N3 is also absorbed to reach the destination B. And finally noise N4 is also learned to reach the destination. Hence, it can be understood here that Mr. X can reach his destination point B using the path 1 as 1, 2, and 3, along with some path deviation in form of N1, N2, N3, and N4. However, path 2 is the new data for Mr. X. And he is not trained on path 2. And if he is at point 5 on path 2, then he fails to reach his destination. Similarly, path 3 is the new data for Mr. X, and not trained for the same. Hence, if Mr. X is on any point on path 3, then he fails to reach his destination. Hence, it can be observed here that Mr. X can manage to reach his destination B using path 1 and accommodating some sort of noise, but fails to reach the destination if using any new path, like path 2 or path 3. This is the case of overfit machine learning model, where model learns and predicts correctly to the training data and noise only, but fails on new data. Now, let's understand the concept of underfit model. Say Mr. X is trained on all three paths, that is path 1, path 2, and path 3, and along with noise as N1, N2, N3 and N4. However, there is one missing information or data, that the road to destination B is closed after 5 p.m. In that way, Mr. X fails to reach his destination due to training with missing data information. This is the case of underfit model. Then how to get a well-trained machine learning model? An underfit model is not usable as it's not trained with complete data set or trained for a shorter period of time, that means less number of epochs. And an overfit model is good for training data set only. To counter this, a good fit model is one that is trained on a large set of data for sufficient number of epochs, using the reasonable mean square error as the training termination. The data set should cover the normal range as well as the extreme ranges on either side. Now, let's take some real-life example of overfit model. Consider the case of learning the multiplication table from 2 to 5. And note here that the model learns the table only and not the multiplication table generation method. Therefore, the multiplication table data from 2 to 5 can be predicted at any time on demand without fail. However, when it comes to generate the multiplication table of 6, the model fails, as it is trained for 2 to 5 only. This is the case of overfit model that produces output correctly to only trained data, and fails on prediction when given some new input data. Now, consider the case of underfit model. Here the model is trained with missing data information, and, as well as without learning the table generation method, just like before, missing data information are marked as red color. The model is trained with small part of the data and with less number of epochs, or MSE, that is mean square error is compromised to a higher value. Hence, it can be said that the model is trained improperly. And, surely the model will fail in correct prediction here. This results in underfit machine learning model. To counter the issue with overfit and underfit model, generalization technique is used. Generalization technique enables a machine learning model to predict well to unseen input data. The prediction to unseen data should be reasonably correct and justified. Generalization techniques help in training the machine learning model with well-shuffled data set, and ensure that entire data is exposed to the model during training session. Also, the data set should cover the normal range as well extreme ranges on both sides, that means on lower and upper side both. In other words, the data may contain some outliers on either side of the normal range for robust training data set and training of the model. Generalization capability in machine learning model is achieved using k-fold cross-validation technique. As already discussed, generalization enables model to predict well to unseen data set. In k-fold cross-validation technique, the data set is divided into k number of folds. Popular value of k are 3 and 5 normally. Say, if k is equal to 5, the entire data set is divided into 5 folds of equal sizes, as k1, k2, k3, k4, and k5, and k-1 folds are used for training the model. The trained model is then tested using the remaining one of the k-fold. As here, k1, k2, k3 and k4 are used for training, and k5 is used for testing of the model. In next iteration, k1, k2, k3 and k5 are used for training, and k4 is used for testing the model. Similarly, k1, k2, k4 and k5 folds are used for model training, and k3 fold is used for model testing. Then, k1, k3, k4 and k5 folds are used for model training, and k2 fold is used for model testing. And finally, k2, k3, k4 and k5 folds are used for model training, and k1 fold is used for model testing. The k-fold cross-validation scheme can be understood in given diagram here. Please note that the value of k is taken as 5. Now, take a numerical example of k-fold cross-validation using linear regression. Say the data set size is 10 here. The target machine learning model is linear regression model. Take the k-fold cross-validation value as 5. That means, the data set is to be divided into 5 folds. This is the data set used for linear regression. X is the input and Y is the output. Therefore, a regression between X and Y is sought here as a machine learning model. This is the target linear regression machine learning model equation. The target is to find the optimum value of B0 and B1 using 5-fold cross-validation. The data set is divided into 5 folds and labeled as K1, K2, K3, K4, and K5. In first iteration, K1, K2, K3 and K4 folds are taken for training and K5 fold is used for testing. The value of B0 and B1 are shown here in linear regression equation. Next, K1, K2, K3 and K5 are used for training and K4 is used for testing the model. A linear regression equation is shown here with B0 and B1. Then, K1, K2, K4 and K5 are used for training and K3 is used for testing the model. A new regression equation so obtained is shown here. Further, K1, K3, K4 and K5 are used for training and K2 is used for testing the model. Again, a new regression equation is obtained and presented here. And finally, K2, K3, K4 and K5 are used for training and K1 is used for testing the model. And, regression equation so obtained is presented. All the regression equations are summarized in the presented table with respective training and testing k-folds. A final linear regression between x and y is obtained by taking mean of b0's and b1's value. This is presented in the last row of the table. To conclude, it can be observed here that, the k-fold cross-validation technique should be used to get a reasonable machine learning model, so as to get correct predictions.